Today on How It's Made. Needles and pins. We get straight to the point. Architectural mouldings, adding bling to your building. Locomotives. We track down the production line. And clothespins. Pegs to you and me. But first, throughout history, sewing needles have kept things from falling apart at the seams. From primitive times when needles were made of bone to today's thin steel versions, sewing needles have played an important role in our lives. For many years, this simple tool made it possible to clothe an entire family. Today, when most clothing is factory-made, a sewing kit remains a household essential. When things start to unravel, a needle and thread offer a quick fix. Sewing needles begin with thin steel wire. Machinery uncoils two spools simultaneously and pulls the wires across guide wheels and into narrow passageways to remove kinks and straighten the wires. And then cutters slice them to the length of 2 needles. The wires exit into shaking chutes and fall into bins in neat piles. Each one will be used to make 2 needles. This grinding wheel turns, and at the same time, an overhead wheel revolves in a different direction to bear down on the ends of the wires and grind them to a point. Sparks fly from the friction. It takes up to 6 grindings to make the tip sharp enough. Then the wires head down the line to a series of stamping machines. The first one flattens each wire at midpoint to form 2 needle heads. The next stamping device punch cuts 2 eyes, 1 in each head. The third machine cuts the wire in 2 and trims excess material from around the needle heads. The needles fall into a bin. In 3 quick steps, the steel wire has been transformed into 2 sewing needles. Next, they toughen the metal by first baking the needles in an oven and then quickly bringing down their temperature. The temperature shock hardens the needles. They cover the needles with glycerin oil and a polishing powder before they wrap them in a bundle of plastic and cloth and stitch it up. They roll a layer of leather around the bundle of needles. The package then goes into a special rolling mill. It spins in this machine for 2 days. Inside, the needles agitate with the polishing ingredients, and they emerge looking much smoother. Then it's into a washing machine for a scrub with soap and water. This removes the polishing residue to prepare them for electroplating. Electroplating gives the needles an outer skin of corrosion-resistant nickel. The needles now move forward into a sorting system that ensures the needles are pointing in one direction. An inspector examines the needles for flaws and sorts out the defective ones. They dip the eyes of some needles in a gold bath and apply an electrical charge, so the gold gravitates to the nickel and adheres. A little gold around the eye makes them stand out, so these needles should be easier to thread. Meanwhile, the production of pins is well underway. Gas jets melt glass into tiny droplets, which stick onto the tops of the pins as they roll by. The glass hardens in seconds, going from transparent to opaque. And these glass-headed pins are now ready for hemming and other sewing jobs. The pins fall between 2 revolving cylinders. The space between the cylinders gradually narrows. This sorts the pins by size as they drop into various bins below. Now all that's left is the packaging. The packaging line is entirely automated. Robots drop sewing needles into grooves in plastic packages, and the packages move forward. The timing is flawless, obviously with pinpoint accuracy. Finally, a transparent cover showcases this product's many selling points. Exterior mouldings can transform an ordinary structure into something grand. The ancient Greeks were the first to demonstrate this with elaborate carved mouldings on temples. Today there's no need to spend long hours carving mouldings. Fabricated synthetic versions are now available to give your structure instant appeal. Architectural foam mouldings trick the eye. They look like stone or wood, and it's all a carefully crafted illusion to impress the neighbours or passers-by. They start with a large block of foam. It's expanded polystyrene, or EPS. They activate a hot wire foam cutter, controlled by computer software. It melts its way through the thick foam block to make very precise and intricate cuts. This computerized hot wire is cutting out pieces of architectural trim for windows or doors. It carves in an economical way to minimize waste. It's work done. The hot wires rise, leaving a trail of smoke from the burning process. A worker then pushes out the mouldings. Each piece of architectural trim is 2.5 meters in length. The hot wire now carves an elaborate fluted column, 1/2 at a time. This is a Roman-style column. Once carved in stone, it's now being replicated in foam. And this old-world look can now be achieved with minimal physical effort. To make an arch, they use a hot wire shape instead of a computerized straight wire. They position it in front of a curved piece of foam. Rubber drive wheels push the foam through the hot wire. These wheels have been preset to accurately steer the cut. The result is an arch that will be a perfect match for the linear trim produced earlier, so they'll fit together seamlessly. They use a carved foam wedge to emulate the keystone, a piece used in stone arches to lock the parts together at midpoint. A worker now wraps the cut foam mouldings in fiberglass mesh. Pre-infused with glue, the mesh instantly adheres to the foam. This mesh adds strength to the moulding, and it also makes it crack resistant. Next, cement flows into a hopper and onto the mouldings below. The mouldings are driven through a template with the same contours to apply the cement evenly on the surface and the sides. This is no ordinary cement. It's a pre-engineered mix, fortified with a special resin to create a durable coating for the mesh-covered mouldings. A worker then transfers the mouldings to a rack to cure for a minimum of 24 hours, before getting another coating of cement, this one with a much finer texture. It's much trickier to apply cement to an arch-shaped piece of moulding, so they take a more hands-on approach. The employee scoops the cement onto the mesh foam semicircle. He then moves the custom-made template over the moulding, instead of pushing the moulding through it. It's a better way to evenly distribute the cement on a curved surface. After carving, meshing and 2 layers of cement, this arch is now ready. For smaller orders, they also apply the cement manually. There's no need for a machine setup when there's only 1 or 2 columns to be coated. Guided by a track on the side of the table, the worker slowly draws the template down the Roman-style column, to apply the cement to the foam and make it look like stone. The second layer gets extra attention. He rubs the cement into the grooves for complete coverage and then pulls the template across once again, this time lightly skimming the surface to produce a finer texture. And now these mouldings are ready to add detail and definition to a structure. With these techniques, Rome really could have been built in a day. Coming up, we keep on track with locomotives. Then take it down a peg with clothespins. See you after the break. A locomotive is the powerful vehicle at the front of a train, which pulls the carriages along the track. Sometimes there's a second one pushing from behind as well. Passenger train locomotives are smaller and designed primarily for speed. Locomotives pulling freight are significantly larger and stronger. Heavy hauls are mammoth freight locomotives designed for North America, where tracks are wider and stronger than in most other parts of the world. The smaller yellow locomotives are for the European market. The larger grey ones to the right are heavy hauls. Workers weld together massive pieces of steel to construct the locomotive's structural underframe. At each end, they insert a giant steel pin through a hole in the underframe's floor. For now, they weld the pins partially to tack them into position. Next, lifting and maneuvering it with giant trunnions, they flip the underframe so that the protruding side of the pins is facing upward. Then a crane system transfers the underframe to another area to complete the welding. The pins require exceptional bonding because they connect the underframe to the wheel frames. An automated welder circles each pin repeatedly, progressively building up a 25mm thick weld. They make the same size weld on the other side of the pin. All the welded steel parts are exceptionally thick, rendering the underframe strong enough to pull 450 metric tons. Next, they install the air reservoir and pipes for the pneumatic brake system and a 20,000-litre fuel tank. Then they assemble the locomotive's 6 traction motors. Each one generates 750 horsepower, 3 times more than a typical car, giving the locomotive 4,500 horsepower strength. To build each traction motor, they bolt coils of wound copper in a cylinder called a stator. Then they lower another cylinder, called an armature, into the stator. Regulated by an alternator, the coils produce an electric field that rotates the armature, turning components which propel the locomotive. Workers lubricate the wheels. Then, using a strong press, fit 2 on each of the vehicle's 6 axles. Each wheel is 1 meter in diameter and weighs half a ton. The axle has a large gear that turns both wheels. This finished unit is called a wheel axle gear assembly, WAG for short. Workers install a WAG onto each of the 6 traction motors. The WAG's gear engages with the traction motor's gear, so when the motor runs, that gear turns, which then rotates the WAG gear, which turns the wheels. So now there are 6 WAG and traction motor combinations. Workers divide them into 2 groups of 3, then bolt each trio into a frame called a bogie. So now the locomotive has 2 bogies, each with an air-driven brake system built into it. Until this point, the bogies have been upside down. Now a crane flips them right side up to prepare for the final assembly of the locomotive. They position the 2 bogies next to the underframe at opposite ends. Cranes lift the underframe and slowly lower it onto the bogies. The pivot pins protruding from beneath the underframe drop into the receiving holes in the bogies. Next, they lower a giant alternator onto the deck of the underframe. It powers the traction motors, as well as the control systems and other auxiliary equipment. This 16-cylinder, 4,500 horsepower engine drives the alternator. Next, the operator's cab. It's insulated for sound and sits on a shock absorber system. Then the various electrical hookups, including these thick cables. Each one contains more than 1,000 wires, carrying nearly 10,000 amps. Now a hood goes over the engine and alternator to protect them from the elements. From here, the locomotive goes to another department for paint and decals. The finished locomotive is almost 23 meters long. Fueled up, it weighs 204 metric tons, and depending on the terrain, can haul a train up to 1 kilometer long. All aboard. The first clothespin, or clothes peg, was invented in the early 1800s by the Shakers. It was a cylindrical piece of wood with a vertical notch cut into the bottom. In 1853, an American inventor patented a spring-loaded two-piece lever clothespin. That's the type still produced today in both plastic and wood. This Czech company makes clothes pegs out of beechwood. Beech is ideal because it's hard and durable. When the logs arrive at the factory, an automated bandsaw slices each one laterally into 7 centimeter thick planks. Wood is naturally damp, so it's critical to dry the planks. Otherwise, clothes pegs made from them would repeatedly expand and contract with the temperature changes and eventually crack. First, the planks air dry outdoors for about 7 months until their moisture level drops to 20%. Then the planks go into a kiln for 3 to 4 weeks to bring the moisture level down to between 8 and 10%. The wood is now stable. Workers cut the planks into shorter, more manageable lengths. Then into 7 by 7 centimeter blocks. Next, they feed the blocks into a cutting machine. Its 4 circular blades simultaneously saw through each block, cutting it into 5 pieces. Each piece is 9/10 of a centimeter thick. As these thin pieces exit the machine, workers inspect them. Any pieces with knots or other flaws are removed and sold to a factory that makes mouse traps. The pieces which pass inspection go into an automated milling machine. It cuts each piece into 4 smaller pieces. Then, in each smaller piece, carves the shape of the clothes peg clip on the front and a notch on the back. So each thin piece of wood has gone from this to this to this. The notch on the back will hold the spring that mates the 2 clips and produces the tension they need to grip. The next machine saws 4 lines down each piece, cutting it into 5 identical clips. Before and after. All that cutting leaves rough, splintered edges, so workers now load the clips into a sanding barrel. As the barrel revolves, the clips rub against each other, the abrasion gradually smoothing the rough wood. Workers also add a piece of wax. As the barrel turns, particles rub off and coat the wood, making it even smoother. Meanwhile, another automated machine makes the springs out of 1.5 millimeter thick iron wire. The wire has a zinc coating on it to prevent rust. Watch in slow motion how the machine twists the wire 7 times to make the coil portion of the spring, then bends the end to make the part that fits into the notch. With all the parts ready to go, it's assembly time. Workers load clips and springs into separate chutes of the assembly machine. As each spring drops down, a mechanical finger pushes the end aside to clear the way for a pair of clips to encase the coil. Then it releases the end of the spring into the clip notches. The machine does all this at a rate of 8,000 clothes pegs per hour. The finished pegs drop onto a conveyor belt that transports them to the next machine, which groups them by the dozen. From there it's off to the packaging machine, which is preset to assemble a specific retail format. This is a 36 count package, so they've set the machine to stack 3 dozen clothes pegs. After placing a paper label on top, the machine shrink wraps the package. Clothes pegs may be a rather ordinary product, but let's face it, their reputation is always on the line.
A signed Edgar Allan Poe collection could mean big bucks for Paul and Cindy tonight at 9 in Auction Kings. And there's more money at stake at 10 on Discovery as temperatures drop in all new Deadliest Catch.